the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is yet another video for linear algebra students who are currently going through coordinate systems and who have just learned about coordinates in Rn relative to bases and coordinates of x relative to the basis and the b coordinate vector, all that fun stuff. Basically this stuff right here. If you haven't seen my video on this, or if you're unfamiliar with this concept, I highly recommend going one video back in this video series and watching that discussion. It's somewhat short, but still gets the point across. Now, during that discussion, I really tried to emphasize thinking about the vector space V as an abstract vector space. In this video, we're going to change gears and start talking about somewhat confounding situation where you have coordinates in Rn relative to a basis also in Rn. So you have three things to consider here: the vector x, which is a vector in Rn, a basis for Rn, and the b coordinate vector for x in Rn. And the piece that people often get confused about is which, what means what, right? So with this first example, we're going to hopefully hammer out the details of what each of those things represent. I'll just let the cat out of the bag a little bit here and tell you this vector right here is in terms of the standard basis. That is the basis 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, and so on and so forth. Essentially the perpendicular coordinate systems that we're used to. So if you think of it that way, that the vector x that is not the b coordinate vector, but instead just a regular vector x, when you're talking about a mapping from Rn to Rn, that vector x is always in terms of the standard coordinate system or the standard basis for Rn. And the b coordinate vector is always with respect to a visual from the basis you were just handed b. Again, let's shore this up with a visual. Find the vector x determined by the given coordinate vector and basis. And then I have a link to a little Desmos app that showcases sort of this, but I'd prefer to do most of this by hand. So this is what we think of as our standard XY coordinate system or Cartesian coordinate system. So normally if you're driving a car in, let's say, New York City, you would go over, let's say 2 streets and up, 1, 2, 3, 4, some number of streets, right? It's a rectangular or a square grid. And we're so used to that coordinate system. However, somebody comes in and says, you know what, that's not the coordinate system that I want to work with. In fact, I want to change the basis for your system. Instead of the basis being the vectors 1, 0, and 0, 1, they decide, you know what, a better way to get to somebody's house is not to go over to the right by units of 1 and up or down by units of 1. Instead, we're going to look at this in a very angled view. So our first basis vector will be 3, 3. And the second basis vector is 7, 8, which I should never have done for this drawing, but it is what it is. There we go. That's our new basis. So when we drive places now, instead of going to the right X number of units and up or down Y number of units, we are going to drive along these roads, which are kind of diagonal, right? They're slanted. And this point is the linear combination of those two basis vectors. Recall, the vector X from our vector space Rn is equal to some linear combination of the given basis vectors. However, the linear combination is actually from this coordinate vector here. So we have -2 of those b1 vectors plus 1 of those b2 vectors. Now, if I had appropriately labeled these, which I didn't, so this is the b1 vector and this one is the b2 vector, that means to get to the vector x, we'll go back 2 in the b1 direction. Well, b1 is that first red vector, the shorter red vector. We're going to go backwards 2 units. So what you see in blue there is us driving backwards 2 units in the B1 direction, and then we're going to go up 1 unit in the B2 direction. Now the B2 direction is this vector right here, so I'm just going to go ahead and measure that out. And there we have it. We land somewhere right about here. Now I'm obviously measuring this out a little bit, and I don't know how accurate my measurements were, but we went backwards 2 in the B1 direction, and then we just went forward in the B2 direction, and we land right there. That is our vector x in terms of the standard basis. Now visually that vector looks like 1, 2, right? Over 1, up 2. However, let's see if that's actually what it is. Well, I know mechanically it's going to be -2 times the B1 vector, which is 3, 3, plus 1 of the B2 vectors, which is 7, 8, which is actually 1, 2. Thank goodness it worked out. So this full example right now showcases what's happening in the background with these 3 objects, x versus the basis b versus the coordinate vector x in terms of the basis v, which we also call the b coordinate vector. B is kind of the easiest to understand of the group. B is a brand new basis, not the standard basis. It's kind of a new way to drive the streets on our 2-dimensional graph here. Rather than driving things horizontally and vertically, we're driving things kind of at an angle. And rather than measuring things horizontally and vertically, that is, go over to the left or right so many units and up or down so many units, instead we angle our view and say, well, no, just go in the B1 direction so many units, and then in the B2 direction so many units. You can still get to any point on this coordinate system using B1 and B2 because they're a basis for r squared. So that's the idea of the basis. And then the B coordinate vector is the directions along the basis B, the brand new basis, if you will. So that's how you get to your destination using the new basis B. The vector x is how we get to our destination using the standard basis. You can see using the standard basis in this case, we would go over 1 and up 2 units to get to that vector x. So that vector x is 1, 2. But again, using the new basis b, we would go back 2 steps in the B2 direction and then forward 1 step in the B2 direction. You still land at that vector x. Now, I'm not telling you that that new basis is an easier basis to work with. That's not the point of this example. This example is meant to get you used to working in different bases and transforming back and forth between a new basis and the standard basis. Now, I do want to showcase what this sort of looks like, and I'll do so using Desmos here. You can see the address up above, so you can directly go there if you want. But what I'm going to do is just showcase, here's our 2-dimensional vector with respect to the standard basis. You can see that there's nothing really weird here going on. I'm going to move this to 1, 2. That's the vector we're interested in our current system. Now, somebody comes along and they create a new basis for this Cartesian coordinate system. Remember, our old basis is the standard basis, but somebody comes in and says, nope, I've got a new basis B. And that new basis, let's go ahead and adjust it. It was 3, 3 and 7, 8. So I'll just adjust this one as well. And I'll turn on those basis vectors. There we have them. It's actually the same basis vectors we saw earlier that I drew by hand. It's just much easier to see them here. Now, the question is, how do I drive using only the streets built from these basis vectors? How do I drive to get to 1, 2? That is called our B coordinate vector. And we knew that from our previous work, we'd go back 2 units in the B sub 1 direction and 1 unit in the B sub 2 direction to get to that same spot. Just to show you, because I'm not a big fan of this part, that is the B coordinate vector, and it doesn't look like it has anything to do with this image, and that's why I don't like to showcase it here, so I'm going to turn it off. But now you can play around with these all day long. You actually don't have to type in values. If you want to change your coordinates, let's say your B1 basis vector is 5, 1, and your B2 basis vector, let's just move it over here to -1, 5. Let's do that. Well, how do you drive to the point 1, 2? Well, you go over a very small amount in the B1 direction and go up in the B2 direction. Notice all I did was tilt the standard basis here. If you want to know how far you go in the B1 direction, you could actually showcase the B coordinate vector. You would go 0.269 units in the B1 direction and 0.346 units in the B2 direction. I'm going to turn that back off. If I change what my standard coordinate is, and I change both bases to something more interesting, yeah, something like that, that's perfectly fine. So remember, the solid blue and the solid red are going to be the new standard or the new bases. To get to that 0.33 in our standard coordinate system, our B coordinate vector has to go forward in the red direction a certain number of steps, and then in the blue direction a certain number of steps. It goes in the red direction 4.5 steps, and in the blue direction 1.5 steps. Again, that vector drawn on this vector space is probably not the best visual, but at least the other pieces are. Now back to the examples. Find the vector x determined by the given coordinate vector and basis. Remember, that coordinate vector is just the set of all weights on the linear combination of these basis vectors that will generate our vector x. That is, the vector x is just this summation or linear combination right here, which when you do the mathematics, and barring any arithmetic mistakes, is 10, 8, 12. Something I want to draw your attention to is that we actually have seen right now a theorem we're going to create in the future. We know from matrix vector multiplication that that linear combination up above can be written as a matrix times the B coordinate vector -1, 2, 3. And later on, not in this video, but later on, we're going to call this matrix by a very special name. Right now, you could just call it the matrix of the basis vectors. More than welcome to call it that. That's kind of what it is. But what if somebody comes in and says, you know what? I don't need you to find the vector x. I need you to find the B coordinate vector for x relative to this given basis right here. Well, again, the same equation still holds. Remember, x is supposed to be a linear combination of these basis vectors. Now, if you take a look at that, this question basically boils down to solving this matrix equation. And I could just create an augmented matrix. And through row operations, we get down to the fact that the vector c, which is the vector of weights on our basis vectors, which we now know should actually be called the B coordinate vector of x. So I'll go ahead and change that here and just say that down below. The B coordinate vector of x is 1, 1, -7. Now the interpretation here is important. Our standard basis is 1, 0, 0, 0, 1, 0, and 0, 0, 1. You want to arrive at, in our standard coordinate system, -2, 7, 2. But the streets you're driving on are not the perpendicular streets 1, 0, 0, 0, 1, 0, and 0, 0, 1. Instead, they're the streets described by these vectors, 1, 2, 3, 4, 5, 6, and 1, 0, 1. So to get to this point in R cubed, by traveling along these basis vectors here, we're going to go ahead and travel along the first basis vector 1 unit. Then, once we reach that spot, travel along the second basis vector 1 unit, and then travel in the direction opposite the third basis vector for 7 units to arrive at this vector -2, 7, 2. Now, obviously, I don't want to draw that out. That's a 3-dimensional drawing, and if you've ever seen me draw 3-dimensional drawings, you know why I'm not going to draw that out. Now, before we leave this video, I want to talk about corresponding statements in isomorphic vector spaces. If you don't know what an isomorphism is, please go back 2 videos in this series to watch the very first video on coordinate systems where I talk about isomorphisms. Essentially, they're like invertible functions. And that's what we're doing here. We're starting in a very abstract vector space and moving into Rn. And before I go through this table, I want to credit it to the author David Ley. This is actually from his text, and I think it's a great table. So with abstract vector spaces, we have, well, vectors, right, in our vector space. But they get changed over into Rn as B coordinate vectors. So as long as u, v, and w are in the vector space V, then the coordinate vectors u sub b, v sub b, w sub b are all in Rn. And vice versa, by the way. Also, if w is in the span of the vectors u and v from your abstract vector space, then the coordinate vector of w is in the span of the coordinate vectors of u and v with respect to the basis b. And again, vice versa, because this is an invertible process. It's an isomorphism. Step C actually is kind of repeating step B. If w is a linear combination of u and v, then the coordinate vector of w is a linear combination, in fact, the same exact linear combination of the coordinate vectors of u and v. Part D there just says, hey, if you've got a bunch of linearly independent vectors from your abstract vector space, guess what? This is kind of the coolest part to me. Their coordinate vectors will also be linearly independent. If you have a set that spans your vector space, V, then the coordinate vectors for those vectors from the vector space V will also span the vector space Rn. And that kind of implies, sort of, the last one. If you have a basis for the vector space V, the coordinate vectors for each of those basis vectors will also be a basis for the vector space Rn. What this is basically saying is, if I start in a very abstract space and I need to do a bunch of algebra in that space, but it's just very challenging. Maybe the space is really just difficult to deal with. Maybe you have to use calculus in that space and you don't want to. You can transform it over via the isomorphism into Rn by transforming each of those vectors to their B coordinate vectors. And in that familiar space of Rn, you do all of your mathematics there. And maybe the mathematics is a lot easier. Maybe it doesn't involve calculus and instead just involves algebra. By the way, that does happen. That's called a Laplace transform. All right, that's all I'm going to do in this video. Stay tuned because the next video is going to be dedicated to identifying what this matrix here is. We'll give it a name and we'll play with that matrix quite a bit. I hope to see you there. Have a great day. Be an awesome human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Yes, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.